New room. I think anyone else is coming?
Computational and
Yeah, that's true.
flashback.
Oh God, tensors.
Yeah, I used to sit
In the very back. Yeah, makes sense. So do you have the Anaconda open?
my computer's dead, so I'm waiting for.
Oh yeah, no worries, no worries. We'll talk a little bit briefly about like what we do when we do data analysis first.
How are we doing Excel?
You can do it in Excel.
I want to learn Excel because I know Python, but I don't know Excel.
Yeah, you're welcome to do both. We can do it in Google Sheets. We can do it in Excel. The major difference will be doing the chi-square fitting itself. If you want to see how that is done underneath the hood, I think it's easier to do in Python because then you have this the background. If you want to look at the data first, which is what we'll start with, of course, and construct something like a chi-square in Excel, that's the best place to start. But once you start doing parameter fitting, and it's not a line, it's easier in Python. So we'll start with some of the more basic stuff in Excel.
I was curious about Excel because intermediate saying use Excel, and I don't know, and I just opened Python.
Yeah, no, I mean Excel. I use Google Sheets for like all of my nerd work, and to first approximation, Excel is great. If you just need to do very simple tasks, Excel has the tools built in and the plotting capabilities right there. If you move outside of physics and you go into any sort of like biology or chemistry, or even like geology, and then this is probably not true generally, but for a large fraction of those sciences, they learn basically Excel only, or something called R, which is a sort of an easier programming language. There is a transition to more Python, and that's why we start computational in Python, and we try to, 1500s in Python as well. But that revolution towards Python has not been fully integrated by all of the physical sciences yet. So if you want a job, you should know how to use Python and Excel. Excel probably for more types of fields.
Yeah, I want to learn Excel.
Yeah, let's go. Okay. All right. So let's start then. I'm going to actually share my screen here. I'm going to share screen 2. And let me know if you see this. Unknown data. Very good. And so you should be able to download that. And so the first thing that you want to do, do you have Excel on your thing or you have Google Sheets? What do you prefer? Okay, then let's use Google Sheets. Yeah. Opening, what do you mean that? Okay. Okay. So we're going to do a couple things today. If you looked at the homework, sorry that I posted it kind of late. It's basically 2 different data analysis type tasks. And the second one is really, it's less structured perhaps than some of the other ones that we've done before. And it's more interested in you developing your investigative skills, right? And so the first thing that we do when we get data is we look at it. I know that seems silly to say in that, sort of a flippant fashion, but it's not. So the first thing that I'm going to do is I'm going to pull up, and I'm going to pull it up here on Excel. We'll put it up there, but if we want to mess with it as a group, we can mess with it in either language. Okay. So here's the data. Okay. And it has X, Y, and sigma. Okay. So let's see if I did this properly. Okay, good. It doesn't have the generating function underneath it, which is very good. So I know what the generating function is, but you don't. And this is very similar to how we live our lives in the physical sciences. Sometimes we take data and we simply need to fit it. We need to find the trend. And so as scientists, one of our responsibilities is to do hypothesis testing. And chi-square, as we talked about last week, is a measure of our ability to do hypothesis testing, right? So what is the first hypothesis? Exactly. So the first hypothesis is always the null hypothesis. Let me write this down. So something that we tend to call H0 is the null hypothesis. And what does that look like?
It's just like,
Yeah, exactly right. So we just say that y is just a constant. Okay. So in order to do anything meaningful, we have to first disprove the null hypothesis, right? That's always our first rule when we do any sort of testing scientifically. So how do we go about doing that? Here's the data. What do you think? What's that? Yeah, let's start with the graph. That's always the easiest thing to do because I look at those data points and I don't know what the fuck they mean, right? So here's what we're going to do. We're going to start here. We're going to scroll all the way down to the end. It goes from 0 to 10. Oops. And then I'm going to right click it. What's that?
oh, the next guy.
Oh,
Yeah. Let's see if I can do a, oh boy, insert.
like, it's kind of red. You red, you red, you red.
Oh, so like A1 and B1.
Yeah.
Okay.
Yeah.
So you ask a question.
I do highlight it. So, oops, that's incorrect. Let's go to change here, XY scatter, and I'm going to do this one. Oops. Why is it doing this?
Like,
Hold on. Let's select the data here. Okay, so here's series 1 and here's series 2. So let's delete series 1 and we're going to use X values. And we're going to set them equal to A1 through, oh, fuck. All right, well, that'll be fine. Okay, and the only thing that you have to do is when you go into here, oops, is that you want to do, let's see if it'll do that. Nope. Howdy. Hold on, let's select the data again. A1. I'm just doing a shift here down to there. Okay, so that should be the same amount. Here's series 2. Okay, there we go. So what do you see?
There's definitely some correlation
What do you mean there's some correlation? What do you mean by that?
between X and Y.
Like, it's not.
It doesn't immediately look like a flat line. So that would be a test of chi by I to determine whether or not this thing looks like a flat line will work, right? Okay. So now what do you see? That's the first part. We're gonna come and we're gonna actually do these scientifically, but then the question would be, okay, so what do you see instead? Positive slope. Yeah, it looks like it's increasing to the right.
Yeah, it's like the 9 the best fit from what I can see. No, that'd be going into a polynomial. We want to do a line.
Okay. So you want to do a line or do you want to do a polynomial, right?
I think we should use on first. We should,
Yeah,
for a line of best.
start with the line and then go to polynomial.
Okay. Okay. So you can do a couple different things here, right? You can ask a few questions about the line. Where do you think the y-intercept would be? Yeah, probably around 0, right? So it doesn't make any sense, for example, if we are going to do some parameter testing, you wouldn't then choose to investigate this area, right? So you would maybe compare between -1 and 1 or maybe -2 and 1, and see where the best y-intercept is. Does that make sense from the data? Okay, and then you said it's a positive slope, so we're not going to investigate any negative slopes, right? Okay. Okay, so now how do we go about finding the chi-square for each of these values? For a constant fit. So let's go up here, and we're going to start creating some stuff up here. Let's do the square, and we're going to use H0 here. Good. So what would that look like? So here's chi squared, and I'm going to use I here to think about an individual measurement, not the sum of them all. So here's chi square I.
It would be y of I minus the function
The function of
x
x of
of
I.
in parameter.
Yeah, given some parameter, let's call it A. What?
Is sigma the parameter?
No, what is sigma here?
That is. Is there your confidence level in that measurement or?
Oh.
It's the measurement uncertainty, right?
Okay.
So this is data that was potentially real taken, and therefore it has some uncertainty. And of course, I should have been clear here. The uncertainties that, say that what?
So you divide by sigma
Correct. And,
squared.
okay, so this is generally how we construct the metric, just a single metric, right? And what we're going to be changing here is this. When it comes to comparing chi-squares, we're going to talk a little bit about the importance of degrees of freedom, but we're not going to quite do that yet. Does that make sense? Okay. So the first thing we have to do, we have to take some measurement here, chi-square. And we're going to do this sort of back of the envelope style. So what is our first thing that we want to test? The null hypothesis.
Y.
If y is a constant in the way that you've written, it's not really y, but it's what?
Wait,
I guess x.
If f is a straight line, if it's a constant, right? So this is the one that we're testing here because we can't change y. Okay, so in H0 case, what are we writing here?
what's a yi minus?
Or.
Yeah, well, what's the function?
Do you want to say f?
Or is that q? Oh, you want, you're doing it.
Okay. What do you mean?
Generalize it first before you pick a slope. Before you pick
I was gonna say like q, just make it q.
Sure. Yeah, I'm gonna use A here because that's the parameter. Okay, and I'm gonna use A0 because it's gonna be a vector of A's.
Mhm.
And notice there's no dependence there on X. Right? Oh yeah, I'm just, okay.
Mhm.
Is that it?
Oh, and you're writing. I thought you were gonna write that f equals a r.
Oh, no, sorry. Is that it?
Divide.
Oh, divide by the experience. Well,
Good. Okay, so how do we do this?
in Excel?
Yeah, so we're gonna do everything in Excel for the first couple ones, right? And then we're gonna let a computer do it. What? You could do Desmos if you wanted. You could, plot some slopes and see how they fit. And I'll also show you that there's an automatic straight line fit through the data that gives you an R and it gives you a chi-square. But in order to get the intuition of how we build these tools first, right? Even when you get to Python, the smartest thing to do is not to build this from scratch. There is a procedure called, what is it called? LMSQ fit, which is the method of least squares fit, right? So that's already built for you. You just give it a function and you give it the parameters and it does it in like this. But in order to understand how that works and to see how these things pick chi-square, right? Moving from something like the most straightforward algorithm, which would be the method of least squares, to something more advanced, which is a gradient finding method, like the Levenberg-Marquardt fit, which is just another name for how to jump down to the place that you're most likely to have the right parameters. You'll want to understand both of these. We haven't really talked enough about random numbers to get into the more advanced stuff, which would be called Markov chain Monte Carlo. But those are really cool. So if we want to come back to them at the end of the semester, that's the best way to do any sort of this data analysis. Okay. So what do I put here? No, we're going to measure each one of these. You don't need to, because when we do the sum, they are squared. Right? Because if we recall here, this is only the individual one, and I'm going to need the total chi-squared for the data. Yeah, so we can do that right here. And so I'm going to start with equals. And I know that it's going to be squared at the very end. So I'm going to do that right now so that I don't forget. And then, cállate la boca. Okay, so now I go in here. Also, sorry, this is really, really small and my eyes are horrible. So let's do this. Why not plus? Why for no plus? Oh, it's probably upset that I haven't finished this. Hold on. Let's do this first. And then let's do this. I will say that Excel is not my favorite. But we're learning. We're learning. Okay, good. So what's this? Equals. Okay, so everything's squared. Good. And what else? Right. So which one of these are we grabbing?
One. Yeah.
Okay, so B2 is our Y1. Good.
Yeah.
And then what?
Minus whatever we put for A naught. I just like put like in like a different color. It's A naught value. I don't know. But the A naught value, and I just like said it was the
Okay, so let's make a choice here, right? You're choosing 2.
Yeah.
Okay, that's going to be the constant. Okay, and then what? Are we done? Sure. Yeah, you could do around this one here.
then divide that by C2.
And you're going to put C2 right here. And then we're going to put this one here. Let's go. Is that a bad thing? Are we scared? No, we're not scared. Okay. And so the great part here is that instead of putting it all into your calculator, and let's make sure that this is clear too. So this is H0 and we're doing A equals 2. Right? And you can just, if you want to make this look pretty, you go up to there. Right? Okay. And so now let's go all the way down. And all you have to do with Excel is simply click the button here on the right-hand side. You'll see that there's a little button with a square. Just pull that to the bottom and it'll apply the same formula at every location. What? That's crazy, right? So this is sort of the power of the Excel because you can apply many things at once. Okay.
Yes.
Mhm. Yeah. So just here, you see where it is on the bottom right-hand corner? And you see how my thing goes from a hand, right, to this, a little black square. Oh, sorry, a black cross. Good? You got it. Okay, so now what do we do? You have to sum, right? And you're like, oh, fuck, that sucks. Well, okay, hold on. Just because the very first one is very big doesn't mean the rest of these are very big, right? Look at all these. What? You have 700? I have like 5,000. Watch this.
Oh yeah, there's like.
So here's sum, okay? And all we have to do in the sum is just drag all of these values. And you don't want that first one because that's not relevant. Okay. That's a big number.
Yeah.
Okay. So let's go ahead and look at the data. Here's the data. Oops, let's go back a little bit. Fuck off. Oh God, I'm sorry, hold on. There we go, that's better. Let's have a look at the data itself. What do we think about it being equal to 2? It's okay.
Um,
Where did my water go?
Does control up and down, or is like the entire column starting from that point down, or that? So like, it's really big, you have like 1,000 data points, you don't fit it all that.
Okay. So what do you think? Does 2 look like a good fit?
No.
No. Okay. If you do it once and you don't like the number, are you done?
No, you can test that with.
In fact, you have to test other numbers, right?
Yeah.
So in fact, the way that we're thinking about each one of these is that we are going to do experiments in which we compare one hypothesis to another. Right? Okay. So even the null hypothesis that y is a constant, we have to compare it to maybe some friends. So what do you want to compare it to? What's another choice for A?
Like 3.
Okay. Like 3?
We have to test.
other people-
We have to get a comparison, right? So this is not saying, for example, that because we just selected A arbitrarily. Now, typically what you do is you'd fit, right? You'd fit it to the data and you find out what the best A was. We're doing this back of the envelope first with Excel, and then I'll show you how we fit the line in Python in just probably 15 or 20 minutes. Okay, so let's copy this. Let's go over 1 here, and we're going to call this A equals 3. Okay. Let's do the same thing here. I'm going to pull this over 1, right? And look what happens. It gets really upset. So you can usually copy things over left and right. Let's undo that though. And let's go back to this one here. And what I'm going to do is I'm going to say, keep the column, but allow the number to change. So please look at what I'm doing here. You do a $sign. That means only use the B column. And then when I go over here to C2, I say a $sign as well. That says only use the C column, right? Okay. So now when I drag it over, it won't explode on me. And all I have to do in here, in the second one, is simply change this from 2 to 3. Okay. All right. So now let's drag this one down. Right to there. Okay. And then let's bring this one over to the left, and it'll also take the sum next to it. Okay, so which one of these 2 numbers is bigger? The one on the left is bigger than the one on the right?
What was the left value again? Or the roughly not value?
No. Look at the actual numbers here at the very bottom. Which of these 2 numbers is larger?
Wait, oh. Oh, yeah, you're right. It's the other way.
Good. So which one of the 2 hypotheses, A equals 2 or A equals 3, is better fit to this data? We do want smaller, right?
Yeah.
Okay. So 3 is a worse fit. Okay, so now what do we do?
We try a smaller number.
Right. So we know that heading away from 2 was worse. So let's go below 2. And this, you may recall from computational, is very reminiscent of the bisection method, right? Which is where you're just trying to cut smaller and smaller and smaller. That's definitely a way to do this for a 1 parameter fit. Okay. So let's do it again. And in fact, I'm going to do it, I'm going to copy, and I'm going to put it right here. And I'm going to make this A equals what? Good. That would be a very reasonable choice, right? Okay. So how do I do this? Well, I can just take this object here. I can still drag it over 1. Can I? Hold on. Copy, paste. That'll work too. And here I'm simply changing it to 1. Good. Look at that. Now I drag it all the way down. And I just copy and paste this one. Okay. So which of these 3 numbers is the best fit? 1. Does that seem reasonable? It does? No, it doesn't seem reasonable. Okay, is there anything missing in this data? Well, the X's are down there from 0 to 10.
Error bar.
The error bars are not present, right? Okay, so that's really going to make us sort of look foolish because we've considered all of these points just as what they are, which are points. But we're missing this bottom part of the equation, which weighs how important a certain set of data are. Okay. So we're going to leave this as is. I'm going to pull up Python. Is that okay? I don't remember how to use them. I think it's annoying. I think it's annoying.
Yeah, there are. You kind of have to like. No, it's yeah, it's annoying.
Yeah. So it's 1 word in Python, and it's like a couple different clicks.
Yeah.
I'm going to show you one more thing here. So we're going to leave this up because. Shut up. Okay. I don't know. We'll see. We'll see what that says. We're going to leave this up because I'm going to show you some of the built-in fitting tools for Excel that don't necessarily take into account the uncertainties. Okay. So let's instead pull up our handy dandy either CoCalc if you have it, or I like to use the Anaconda. It's opening somewhere. I'm just on my way. All right. Here we go. And let's make a new one. Okay, what's the first thing we do? Yeah. And do I do that by actually doing it? No. First thing I do is I go to my recent piece of code. I grab everything I think I might need. Doesn't matter what it is. And I copy and paste it because that will never change, except for when it does. But at least now I feel like, okay, I got a majority of them in here. And there's a lot of shit in here that I probably won't use, but I got most of it in, right? Matplotlib as plot. There's numpy as np. I got glob for files. Okay. All right, now what do I do? Run it, get a new box. Now what?
Right. Do you want to?
You just send them.
Very rude. You didn't keep them all? All right, let's see.
I'm not helping them. I'm just getting what I think I'm gonna need, like, laptop, more than. Are we gonna need pandas?
There you go.
Yeah.
I put it all in there.
Import.
Yeah, pickles, pickling is actually really fun. You just like take any variables and you put them into a jar, and then you can you can open the jar later and pull the pickle out. It's pickling, right? You hold on to it for later. Well, no, marinating is different. Pickling is for long-term storage. Marinating is for yummy cooks. Oh yeah, yeah, that's true. That's true. That's true. Okay. Good. So now what do we do?
If we have to get that,
We got to pull the data in, right? What kind of data is it? It's actually not an Excel sheet. It's a CSV. Okay. So how do we do that? Do we?
that's all right.
Yeah, you can just do a CSV reader like this. You can do it a couple different ways. You can do. Let's see, how do we want to load it today? You want to do pandas?
I've always
People
done-
prefer pandas?
I've always done.
Okay.
It's up to pandas. Yeah, I mean, so it's the exact file location.
Yeah.
I'm not.
Yeah, it's not hard to find.
So here's the line. Okay. And the easiest way to do this, of course, like we mentioned, is to grab the exact file name. So how do we do that? Well, generally speaking, you say, oh, I have to find the file and move it around and blah, blah, blah. And that's actually incorrect. What you do is you simply take your file and you move it. No, sorry. Instead of putting the path in, you put it in the right folder. Excuse me? You just upload it to your Python. Okay, sure. Yeah. Yeah. So now we just need the name.
Yeah, unknown data.
Let's see if that worked. Now, how do we know if it worked?
Well, if you ran it, then. And when it gets, trust me, I did do this. I ran
If you ran it, it works.
They would have told me like, "Hey, you can't find it." Just do it all out.
Look at that. Now notice it didn't pull in the graph. So it just pulls in the data, right? How do I navigate with pandas? What do I have to do here? Read. How do I navigate with pandas? Just what if I want all my X's? I want an array called X. What? No, you wouldn't need that. You won't do that. No. This just happens to be the one that we're working in, obviously, right?
How do I upload these to the calculator?
Hold on.
Is that correct? Is that true? Okay. So let's have a look here at what I did first. So this is pandas. Pandas read CSV. Here's the data. And then I asked, what is DF? And notice how it has this line all the way through. Then it has the data separated into columns. It knows the difference between what we call the header and the data. And then, so yeah, it's very smart. Pandas are smart enough. Okay, so then we can just grab each of the three, and it knows how many rows there are. There's 101 rows, but it starts at 0, so there's 102 rows. Okay, and we're only going to use the first 3 columns. Okay, so let's see if that works. Reads 100% confident. Money on the line. Oh, Okay, so let's do the other ones. Let's assume that those work. Let's do copy, paste, paste. And then we're gonna go here, Y. Here we're gonna go S. I know that's bad variable placement, but sue me. Okay, so now what? Let's plot it up, boys. Okay, and others. Okay, PLT dot plot X comma Y. Is that what we wanted? You want a scatter plot. So is there a different thing that we should use, or do we just go in here?
Like, no, it's, I've always done that, like if you were inserting strings and just, oh, so you always do that.
No, I hated that.
I think it's literally just like a quotation mark of. So it's X comma Y, which is so it's that plot.
You don't have to make the lines disappear?
Yeah, no, just for scatter plot,
Okay, that's pretty good.
error bar,
That kind of looks like what we had before.
yeah.
Good. Anything else?
Error bar, so it's-
Error bars. Okay, so now what do we do? Now I claimed that it's super easy. Is that true? All right, so let's go Y error bar. Not plot good. Oops. Okay. All right, so here's the way that it's written. X, Y, just like before, and Y error equals a variable. So it's a keyword because you'll notice that sometimes you can have an X error or you can have a Y error, but the default will be that it has neither. So let's play with this for 1 second. Let's go down here and we're gonna say error bar, and we're gonna get rid of plot. And we're gonna get rid of this point here. Okay. So that gave us the line that we just had. Let's see if we can do it back with the O again. No, okay, line error bar does not have the points. So let's go ahead and look in here. Keyword arguments. Yeah, okay, so it's gonna be marker. Let's do marker equals a circle. There you go. Okay, so there's the points, and now they're connected by lines. And we probably want to unconnect those lines if we can. So here is line style. And I think that the one that we want is solid join style. So, oh wait, hold on. Valid keyword arguments are not good.
Or you could just do F and two of these ones. Instead of-
Yeah. FMT. What does that say?
And I think it said something. F format.
Ah, I see. Okay. Good. So now we got back what we wanted. Okay, and we always want to do that before we throw the error bars on. So now we can do here Y error equals S. Oh.
Y error, not, don't have the OR.
What'd I say?
If you type Y error, then you need the OR.
Yeah, it's just.
Y error.
Yeah.
Oh gosh. Oh gosh.
Oh, you must have to make it.
Okay. So that's okay. How do we fix that? What's that?
Y error is not produced.
Did yours work?
Like you got, yeah, everybody.
What'd I do? What'd I do?
You can't do the exact same thing.
I don't know why you have. But I think it's true.
Yeah, I don't know.
So now let's have a look at the data again. And earlier we claimed that 1 was a better fit to the data than 3 was. Why is that?
Oh, the big error bars.
Because the goddamn error bars get fucking huge, right? So we're running basically a truck through, you know, a wide city street when we get out to x equals 10. Whereas at the very beginning, we're trying to navigate like a flea through the eye of a needle, right? Does that make sense?
Yeah.
It's a bad analogy or good?
Similar.
Thanks. Okay, so down here, it really matters to fit the data. Okay. Let's make some comparisons now. So we have our Excel spreadsheet up and we know that 1 was better. Let's use this and we're going to compare against the null hypothesis, right? So that was H0. Let's talk about H1.
That's the way, why is it gonna should be, or is it saying?
Yeah, you tell me. Is it?
It should be.
Okay, that makes more sense, right? That would be 2 parameter fit.
Yeah.
Now, what do you want to use here?
Well,
You want B to be 0, but there is no B. Okay, but there is no B.
Okay, A1.
A 1 is 0.
Because that is
So what was this before?
We did like 1, 2.
This is 2, and that is what?
Oh, 2.
I don't know, but what does that mean?
that one's just.
Oh,
That was the intercept.
Ah, okay. So A naught is always the intercept, and then A1. Okay, so when we're thinking about this in the context of a polynomial, right? Each one of these individual parameters will go up and up and up by 1 after the other, because A naught refers to how many x's there are. 0 x's, A naught is the y-intercept. 1x, A1 is the 1 component. Now, this will totally break down if we're not using a polynomial, and that type of logic will just evaporate and you can do whatever you want. But just so that we're not confusing ourselves between these two properties, let's look at A0 equals 0 and A1. What? Okay, what does that mean?
you did like,
How would you guess? How would you tell?
well, by eye, I think like going by a 1 slope is too.
How would you tell from the data?
I'm having.
What is slope? Rise over run. So what is the rise over the run? Right? Can't you just take the first data point, say 0, 0, and the last data point 10? This is like what, 0.4? Oh, sorry, 4.
Yeah.
So what's the slope? 4 over 10, which is? Okay, so A1 is going to be 0.4.
Okay.
That's a guess. We're not fitting yet. We're going to get to fitting. Fuck, hopefully we have time to get to fitting. Okay, so let's do that now.
And we gotta meet the.
So we can do this a couple different ways, right? We looked at the data. Let's go back to our. Where'd it go? Oh boy. Shh, 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 shh. Don't hate on my window game. All right, here we go. So let's just do it right here, right? Let's do chi-square. Copy that. I'm going to bring it over. And we're going to call it H1. It's going to be a 2-parameter fit. We're going to say A0 is 0. And A1 is 0.4, right? Yes or no? Okay. So now what do we do? How do we construct this? Copy it, paste it. And what has to change in here? The 3 to become, which is good. Okay, so here's X is over here, right? And we'll need to make sure that we do this well because we don't want to accidentally take things and put them in the wrong spot. So I'm also going to put a $sign. Good. Hey, look at that. Loves that point. See, even in the first point, the chi-squared down. So we're 100% confident it's going to be better, right?
Yeah.
We don't know. We'll see. Okay, so let's go down. All the way down here to the bottom. Okay, we're going to delete this now, or at least move it over. Excuse me, sir. Go away. And then this is our chi-square. Whoa, so much smaller. Okay. So even our first approximation is better. Okay.
I would like to see, how you do your chi-square equation instead of the formula.
Right, because by definition, our f for f of x, comma a, is in this case a1 times xi plus a0.
Yeah.
Right?
Mhm.
Okay. Now what? Yeah, so assume that's a perfect assumption. We in fact will try more things. How do I compare these two hypotheses? The number's smaller, right? And generally speaking, we need to consider the fact that when you get a smaller number, you get punished for the fact that you used more parameters. So what do I mean by that? If you're talking about this, we're thinking about the term degree of freedom, okay? And generally, what we're going to say is that you have some chi-squared distribution. The chi-square distribution has m minus n degrees of freedom. Okay. Oh, sorry, that was backwards. N minus m degrees of freedom, where n is the number of data points. And then this is the constraints. So this is the parameters. Okay. You can do some written work here to show that the expectation of chi-squared, I'm not going to write this for you, but you can look this up. The expectation value of chi-squared should look something like n minus m plus minus the square root of 2 n minus m. What I mean by that is that a value lying well outside of this range would be assumed to be incorrect. That make sense? What is our degrees of freedom here? What's our expectation for chi-squared? I think there's just 100. Maybe it's 100. It might be 101. 98. Good. So n minus m should be 98.
What is, like, so like, what's M again?
M is like how many values you have in your A vector.
So probably means
Okay, so in this case, we have two, okay.
Because remember what we said in class on Wednesday. We have this value called the reduced chi-square. So what that means is if I divide this thing by n, right, I should get a number that's pretty close to 1, because each individual observation compared to the model, if the model's good, contributes something like a value 1, right? Okay, so now if we compare these two, compare m changing from 1 to 2, for example, that's a very small difference. So to first approximation, let's just call this 100. And which of these two values is closest to 100?
Of the ones we calculated.
Of the ones we just calculated, yeah. That's okay. Which of these two models, H0 or H1, is closer to our approximately 100? Yeah, of course it's H1, right? Okay, good. So we did the right thing. So this is disproving the null hypothesis. The null hypothesis is not as good as one in which a line goes through the data. Right?
Yeah.
Okay. So now let me show you a built-in model inside of oops, fuck, where'd it go? Hello. Right, here it is. What? All right. So here's some fun things we can do. Let's go to automate. What happened to my good old-fashioned formulas? Page layout, data. Oh God. Oh God. We did something. Where is this? Okay. Well, this is why I guess we don't do it in Excel anymore. So they used to have built-in line plotting. And now I can't see it at all.
I remember we calculated this in the India lab last week.
Yeah, I mean, oh wait, is it this one? Oh. I just want the 1990 version of. Okay. All right, guys, calm down. Okay, so here's what we're gonna do. Because I can't find those directly, I'm gonna show you how we would do this in a brute force method. Okay, so what does it mean to brute force something? It means you just try the entire parameter space, right? Okay, so here's what we're gonna do. We're gonna build a chi-square map. And like I talked to you about at the end of class on Monday, this is absolutely the worst way to do it But it shows you visually this regime of chi-square interrelationship between the two. Okay, so first thing I'm going to do here is I'm going to create, just for the last one that we did, here's our plot error bar. I'm going to move this one down. And I also want to create a function of the h1 that we just did. So let's do h1 underscore first try, or maybe how do we want to write this? Here. Let's do h1, and we're going to do x comma a0 comma a1, right? You guys remember how to make user-defined functions?
Yes.
Okay, so what is it? Very good. All right, that wasn't so bad. No one cried, right? Okay. So that means that I can go here and I can do a plot. Oh, wait, oops, sorry. And I can do x, comma, h1. Oh, wait, I have to create this first. Excuse me. h1, so that's a new function. And I'm going to do x, comma,
Oh, the eight, 0 and 1.
which are?
Oh, yeah, 8, 0, and then how many?
Good. Okay, so that's the best fit line. Right, yeah, sorry. That's our, of the two models that we tried, that is the one that it came up with. What do you think about it?
It's definitely better.
It's better than the straight line, or it's better, sorry, better than the horizontal line, right? But it's still pretty garbage, no?
Yeah, I think we could try different lines and stuff. Maybe something like a bit less than 0.
Okay, we are gonna do that, but let me show you first how we're gonna brute force it. Okay, so down here, I want to create an array, and let me bring this up for a second. So generally speaking, I need an array of chi-square values. So I'm going to say that chi-square, right? And how do you want this array to be? Maybe np dot zeros. And I'm going to make it a 10 by 10 array. Okay. No, just because I don't want the big parameter space to be super big. Okay. And so what I'm going to do here is I'm going to fill this array up. Okay. So I'm going to say for I in range 10. And I'm going to say the word for instead of fur. And I'm also going to do for j in range 10. Okay. All right, good. So now what I want to do is I want to do that entire thing where I walk through all of the x and I want to add them all up, right? So I need one more loop here where I walk through all of the x. So I say 4k in x, right? Okay. And now I can just do this. I can say chi square, and I'm going to identify ij. And I'm going to do plus equals the value of chi squared. Okay. Now we have to be careful here because this is no longer Python. Okay. Okay. So I'm writing a bunch of gibberish here because I'm realizing that K, I can't use this. I have to use a different one. because this needs to be an index. K in range len. Oops. Okay, that'll work better. So now K will be the index of each of these values. Let's do that there and that one there. Okay. And now we need to be a little clever here inside. So this is where the H is going to go, right? So what do we want to put in here?
Like, so the H1.
Mhm. Yeah, so the reason for doing this is that we're walking along in the parameter space. Okay, so do we want our parameters to go from, for example, I, do we want it to go from 0 to 10? We know that that's the index, but if I look at, say, let's say we're just talking about a naught, how far should we let that run? Yeah, 2 max for sure, right? And maybe -2 to be safe. So, right, so you need what's called a, where did my fucking chalk just, oh, here it is. Okay. So if I want to go from the range of 0 to 10 to -2 to 2, how do I get there? It's okay, I'm gonna do it up here on the board. Good. Start by subtracting 2. Okay. And then change how much it goes up by. So if it used to go up to 10, and now I want it only to go up to 2, but it starts at -2, I really want it to go up to 4. So I need it to go up to 4 and not 10, right? And now I can just do that. And again, that's a slope y-intercept problem. Good. So let's put that in here. What's 4/10? Oh, that's interesting. What's that? No, I'm converting now. I'm converting I. Oops. So watch this. Times I minus 2. That, so this is our y-intercept. Our y-intercept is moving up and down. Just so happens to be moving kind of the same amount that we would expect the actual first approximation to have run, right? I'm not going to use the function. I'm not going to use the function here. I'm just going to plot. I only created that function for the end, right? I mean, I guess we could. Does it, do we want to use the function here? I'm going to use the function now that you said it. Okay, just to make it more clear where everything sits for anyone who's following along at home. So the first one was x, and we're just going to use a single value for x here. So we're using xk, okay, comma. The first one was the a naught, so that's this one for sure, right? Comma. Now we need to convert our slopes, right? Right or wrong? Because we don't want the slope to go from 0 to 10. We want it to go from what?
0 to 1.
0 to 1? Is that reasonable?
I don't think it's two, because it wasn't one.
That's true. Yeah, 0 to 1. 0 to 1.
0 to 1?
Yeah, that's easy.
Okay, so how do I do that? Okay, so let's do j divided by 10. And I'm going to be really careful here that it's a float. I do 10 point. Okay, is this right? Fucking hope so, bro. Ready? Yo! All right, and now what do I do? So here I'm going to plus, I want to look at the chi-square. Now this is going to be a 10 by 10 image, but I can do, oops. Did I do anything wrong? Let's first ask the question, what is chi-square? Nope, all nans. Okay, what did I do wrong here? I'm worried that once you go outside of the range, so what was this, 100? Was it 100 or 101? There we go. So once you get to the very end of the array, Pandas sees that empty space in Excel as nans, and it doesn't ignore them. Okay, so that's better. So I just went to the end of the array. And then I'm going to do here. Okay, good. Let's fucking go, boys and girls. So what does it look like?
What's can we get like a color key?
I think you can zoom it.
Yeah, like I think that it's probably using like the darker areas like one more time.
Okay, let's do a. Oh, I see what you're saying. Okay. Bright color bigger. Yeah. So what do you see here?
One. Thanks, that.
No, the ticks don't match what the actual number is. Remember that we'd have to convert to go back. Okay. Yeah, so here we have I going this way, right? And J going this way. I is this axis, right?
That's right.
And Y is this axis.
One of them is so-
Good, yeah, so which one is which? Here is your,
That's-
yeah, A naught, right? Intercept. And here is, exactly. Okay. So there is a correlation between the parameters, obviously, right? And you could even go in here and you could be a little more specific. You could say V max. Oops.
that's-
No, so what I'm doing here is I'm saying ignore everything above 4,000. Exactly. That's precisely what folks will do. So when you look at this data here, you see that there are just two regions in which the chi-squared is minimum, right? Or the smallest. Now you'd have to compare this one to this one and see which one was the actual smallest. But similar to what we just saw, there's sort of a channel that goes through. And the uncertainty in the parameters that will derive is related to how much uncertainty there is in the chi-square parameterization. So we only did 100 points. You, of course, could do this a finer resolution. You could do 100 by 100 and really dig into it and then pull out the best fit model. So I don't remember what this is. This is 4, 4, and 5. So 5 here would be 0.5. And in fact, I can just do this. Yeah, watch this. So instead of plotting just one of them, I'm going to use the result. And so I'm going to say I was this direction. We're going to start with 5. And in this direction, it was 4. Oh, same line. Good first pick, y'all. Okay, so let's go up and to the right. So this one is what, 7 and 3. Cool. Do either of these look like fits to the model?
No, perfect.
Not perfect fits or not fits?
Good fit. I think the red line fits it better.
You think the red line fits it better?
Yes.
Also says dark. Like,
Okay, so let's do it like this. What was the first one that I said? It was like
I think it's fine for. I think it's 7.
high spread, folks. High spread. It's not callable. It's not chi. Chi is a different symbol. What's that? Chi blocking? Is that what you said? Okay. Okay, so 5-4 is the better choice by far. Correct or not?
Yeah, oh, yes, because it's closer to 1.
It's closer to 1.
it's-
Not 1, but excuse me.
I think that one's better.
This one's blue. And this one's black. Okay, let's do this. Well, no, I mean, it could be that the yeah, so that's the chasm. What was the largest number here? 4,500.
Do you want the smallest, size of it?
Sorry, say that again?
Do you want the smallest size of it?
Yes, we want the smallest chi-square that we can find here. Now, typically what you do is you'd actually like search the array for the smallest chi-square. But I'm just comparing two of them here because I want to demonstrate that neither of these is close to what we want. But it's not 1, it's we don't want a chi-squared of 1, we want a chi-squared of what?
Oh, good.
No? No guesses. No guesses.
So, like,
That would be a reduced chi-square, but that's not what I'm asking. We calculated it, it's on the board. Standing in front of it. Isabel said it a bunch of times.
I don't think-
What we want from chi-squared, in this case, is 100, approximately.
I-
You said the number of points, but I wanted the number of points. 100. What is the number we want? Right? That's right. Right? It's number of points minus m. For a 2-parameter fit, that's 98, which is 100. Right? So if the value that you get is 98 plus minus, what's the square root of 200? Like 15, 12, 13, something like that. So 100 plus minus 12 or 13. I don't know. Does that make sense? Okay. Fuck, we ran out of time again. You can do a different function. Let's do a different function. What function do you want to do here? You want to add another A2? Yeah, so you could do something like this one. Okay. And let's do it here. A2 times x squared. Oh shit. Plus that. Is that right? Okay, we're gonna call this H2. All right. So now what do we do? Yeah, well, one of the first things I'm just gonna do here is I'm just gonna copy this stuff and show an example of how much better it'll look if we just use a curved point. So what's H2? Just give me some examples here for H2.
Like,
Intercept still starts at 0. We like that?
yeah.
Okay.
And like 0.5,
0.5.
yeah.
Okay. Is it curved up or curved down? Okay, so it's got to be a minus, right? I'm gonna do 0.25. Or I'm gonna do 0.2. We'll just see how that looks. Maybe it'll look like garbage. Then I'm gonna comment this out. I'm gonna comment this out. Too much. Okay, let's go backwards. Let's go 0, 2. Okay, that's a little better. So maybe a little bit more. What do you think?
Definition.
Okay, now maybe we start a little lower. Hey, yo! Right? Okay, so you start with a little fucking around, right? And then you have a 3-parameter space that you have to investigate. Now, looking at that valley will obviously be harder because you can't look at pictures in 3D very easily. You can only look at slices. But finding the minimum value isn't that hard, right? You just ask, what is the location of the smallest value in this array? Okay, and then you pull that out and you can plot it. And generally speaking, that's what the point of any line fitting model will do. Does that make sense? Okay, so I need to stop here because we have to go, or I have to go listen to the talk for today.